Good afternoon, class. We are looking at exam 3 review, chapter 3, differentiation rules, chapter 4, application of differentiation. Exam 3 covers from 3.9 to 3.11 and 4.1 to 4.5. And here's 4.1, maximum and minimum values, 4.2, the mean value theorem. So the sections that we will cover. 4.1, maximum and minimum values. Definition, critical point short CP, a critical number of point of a function f is a number c such that f prime of x equal to 0 or f prime does not exist, dne. So the process is, number one, find f prime of x. Number two, set f prime of x equal to 0. And number three, f prime of x doesn't exist. Either look for f prime is 0 or f prime does not exist. In fact, you want to look for both. So we want to find the critical numbers for f of x equals x to the power of minus 2 times ln x. So we are going to use the product rule. This is f times g, so we need f. So we need f prime g plus g prime f. So x to the power minus 2 is negative 2, x to the power of negative 3 times g, which is ln x, plus g prime, which is 1 over x, times f, which is x to the power of minus 2. So let's put them together. This 2, they give us x to the power of minus 3. The first one is very straightforward. I hope you see that you x to the power minus 2 divided by x is x to the power minus 3. You factor out the x to the power of negative 3, and you get minus 2 ln x plus 1. It's important to be able to write it in this fashion. So we are going to write it as this piece over x cubed. So this is the differentiation. And of course, the differentiation, this is the only part that is calculus. The rest has been algebra. So set this equal to 0. A fraction is 0 when the numerator is 0. So minus 2 ln x plus 1 equal to 0. Ln x becomes 1/2. The arrow, x is e to the power of 1/2 precisely, or square root of e. Now, f prime does not exist. In that case, x cubed, the denominator is 0, which results in x being 0. However, that's not an acceptable answer. Why is that? Because if you go back to the original function here, it's x can't be 0 because it's ln x over x squared. So x not only can't be 0, the domain is from 0 to infinity, because when you have composite functions, the one with the highest amount of limitation would give you the domain. So the domain for 1 over x squared is all real numbers except 0 for ln x from 0 to infinity. Therefore, that would become the domain. So that's not part of the domain, and we are done. All right. Formal definition, maximum or minimum points on a curve. Local, also known as relative extreme values. Extrema is the plural of the Latin extremum. A local minimum is the minimum value within some open interval. Local minimum occurs at a point C in an open interval of A to B in the domain if f of c is less than or equal to f of x for all x values in that open interval. So let me give you the second definition, and then I want to go back to the graph. A local maximum is the maximum value within some open interval. Similar to that, local maximum occurs at the point C in an open interval of A to B, so far the same. In the domain such that, in this case, f of c was less than or equal to f of x, in this case, because the maximum greater than or equal to f of x for all x values in the open interval. So if you look at this one, this is a local mean, this is a local max, local mean, local max. So we can distinguish between the two. So peaks and valleys, P is a local max, valley is a local mean. Absolute or global extreme values, or extreme or either maximum or minimum points on a curve. Absolute minimum occurs at a point C if f of c is less than or equal to f of x for all, and that's the key, for all x values in the domain. So when we look at this graph, local mean, local max, local mean. This local mean is also absolute mean. Y, no other point has a smaller y coordinate. Absolute maximum occurs at the point C if f of c is larger than or equal to f of x for all x values in the domain. Again, the keyword is all. Local max, local mean, local max. This local max is also an absolute max. And why is that? Because no other point has a y coordinate larger than that. And again, when we refer to extrema, we mean the y coordinate. However, we should know the exact location as well. The end points, by the way, can be absolute but not local. We are going to move on. All right. We want to find the absolute max and mean values of f on the given interval, where f of x is 1/3 x cubed minus 9x in the interval of -6 to 0. So here's the extreme value or closed interval theory. If f is continuous over a closed interval, a to b, then f has a maximum and minimum value over that interval. So must be continuous, the given interval must be closed. In which case, the methodology is as follows. Method: find CPs, critical points. How do you find them? F prime is 0, F prime doesn't exist. Find f of a, f of b, f of c sub 1, f of c sub 2. In other words, evaluate the function at the end points and any critical points in between. Absolute max is the largest value, absolute mean is the smallest value. So that's how you do that. That is the process. Now, to go back to this continuity and closeness, closeness is given. The very first thing you have to discuss is the function continuous. And if you're claiming it's continuous, why? And you got to be able to come up with a domain. This function is a polynomial, and all polynomials are continuous from negative to positive infinity. Recall, polynomial functions are in the form of f of x equals a sub n, x to the power of n, all the way to a sub 0. So this is degree n, and this thing is leading term, and a sub n is the leading coefficient. A sub n is not equal to 0, n is a whole number. Whole number means 0, 1, 2 to infinity. In that case, the domain is negative to positive infinity. That's what we mean by continuity. If you're claiming a function is continuous, okay, come up with the domain that is continuous. All polynomials, regardless of the degree, are continuous everywhere. So that is established. If this is continuous from negative to positive infinity, must be continuous in the interval that is given from -6 to 0. Continuity can include the endpoints. Differentiability can't. So the very first thing is what? Find f prime. So f prime is 1/3 times 3, x squared minus 9. So that's very simple. By the way, this is a polynomial of degree 3, more specifically, which is continuous from negative to positive infinity, and therefore continuous from -6 to 0. And that's important to understand. Okay. So polynomial of degree 3, domain is all real numbers, therefore is continuous in the given interval. F prime is x squared minus 9. We're going to factor it into x plus 3 times x minus 3. And when we set this equal to 0, we get -3 here, +3 here. F prime dne does not exist, doesn't produce any solution. This is phi, a Greek letter that represents an empty set. Okay. Meaning f prime equals 0 has solutions? Yes. How many? 2. F prime doesn't exist has solutions? No. So those are two possibilities. Now you look at the given interval. Is -3 in between? Yes. Is +3 in between? No. You have to check it, and that's out. So the only one you're going to use is -3. And this, which looks like an epsilon, it's an element of, I'm reminding you about the meaning of this. This is a symbol in set theory for an, and it's read an element of. Therefore, you are going to evaluate the original function at these two endpoints as well as -3. So put -6 in there means put -3 in there means f of 0, just plug in. I mean, this is 0. I mean, just plug in and it becomes 0. So that's obvious. So you evaluate each one, you get -18 here, +18 here, 0 here. Which one is the largest number? 18. So you're going to say absolute maximum is equal to 18 at which pair? These two, -318. What is the smallest number? -18. So the absolute minimum is -18 at this pair. So it's pretty straightforward, everybody. Find the absolute max and mean values of f on the given interval. F of x is x plus 3 to the power of 2 thirds minus 5, the given interval of minus 4, comma 5. Reminding you of the methodology for the extreme value or closed interval theorem. Okay. So what are we looking at? First and foremost, let me rewrite this so you know what we are dealing with. F of x is equal to cube root of x plus 3 quantity squared minus 5. So what are we dealing with? We are dealing with the cube root. As you know, there is no restriction on a cube root. So as far as graphing, just to give you an idea, this is cube root of x, then you move it to the left by 3, square it in. Remember, the portion which is positive gets larger, the portion which is negative flips over, becomes as large, and then move it down by 5 units. It's a cube root. And as you know, the domain of a cube root is what? All real numbers. Therefore, this function, so extreme f is a cube root, is continuous on negative to positive infinity, and is continuous over the given interval of minus 4 to 5. The next step is to follow the steps and find the CPs. So we are going to go with f prime of x, and that means 2/3 x plus 3 to the power of 2/3 minus 1, or negative 1/3. We are differentiating. We rewrite this, so this goes down and takes a positive exponent, and we are going to look at f prime equals 0, f prime doesn't exist. So I'm going to remind you, as far as a fraction is concerned, a fraction of the form a over b is 0 if a is 0, meaning a fraction is 0 when the numerator is 0. A fraction is undefined when the denominator is 0. So is this fraction 0? The answer is no, because the numerator is a number. It doesn't matter, positive, negative, small or large. The numerator is 2, can never be 0. End of this story. If now we go to this part, f prime does not exist. Yes, it can, because we said b equal to 0, so set the denominator equal to 0. F prime does not exist when the bottom is 0. You don't even have to solve it. You can see that basically if x is negative 3, this becomes 0. There's really not much to it. You can go through the process, but it's obvious the answer is negative 3. Is negative 3 in the given interval? Yes. Let's say it were not, you couldn't use that. You would just use those two, but it is, you could use that. So go back to the original function, plug in these two numbers, plug in this number, evaluate. So I'll show you, for example, for negative 4, and I'm going to use this one. So class, I'm going to put negative 4 here, negative 4 here, negative 4 and 3. I get negative 1. So cube root of negative 1. Then I'm going to square it and subtract 5. So what do I get? Cube root of -1 is -1. Square it, you get +1 minus 5. And the answer is -4 here. Then I'm going to put -3 in there. If I put -3 here, that goes to 0, and I just get -5. So there's really not much I have to do. I'm going to put the 5 in there. 5 and 3 gives me 8. So cube root of 8. Square that. -5. As you know, cube root of 8 is 2. So 2 squared is 4. -5 is -1. So those are the values, which means the largest value is this. Since all of them are negative, this becomes the largest value. That's absolute max. This becomes the smallest value. Here's how you write it. Absolute max equals -1 at the pair 5, negative. Absolute mean equals -5 at the pair -3, -5. Sometimes they just want the x, sometimes they want the pair. But please understand, absolute max and mean refer to what? Refer to the y coordinate of the function. Example 22, find the absolute max and mean value of f for the given interval. F of x is x over x squared plus 2, the interval of 0 to 4. Again, this is the methodology. So what are we dealing with? What type of a function are we dealing with here? This is a polynomial function. This is a rational function. A rational function is a function where the top and the bottom are both polynomials. If you recall, rational zeros, the top and the bottom are integers. Now we are dealing with rational functions. So you set the denominator equal to 0, you exclude that, that becomes the domain. So a function f is a rational function is if f of x is in the form of n of x over d of x. D of x can't be 0, and n of x and d of x are polynomials. They both must be polynomials. The domain of f consists of all real numbers except the zeros of the denominator d of x. In other words, set the denominator equal to 0, exclude that, and that becomes your domain. So when I set the denominator equal to 0, that gives me no solution, because the denominator is x squared plus 2. So if it were negative, would be a different idea, but it's plus 2. It can never, ever produce a real solution when you set this equal to 0. Please understand there are two imaginary solutions, but no real solutions. Therefore, the domain is all real numbers. F is a rational function which is continuous from negative to positive infinity. Normally that doesn't happen. You set this equal to 0 and you exclude that, but it happened here. Therefore, it makes it continuous in the given interval of 0 to 4. First, you have to discuss that. So the next step is to take the derivative f prime of x, and you use the quotient rule f over g gives you f prime g minus g prime f over g squared. So let's assume this is f, let's assume this is g. So we have, if we want to differentiate this, the derivative of the top, which is 1 times the bottom, which is x squared plus 2, minus the derivative of the bottom is 2x times x over the denominator squared. You simplify the numerator as follows. These two can combine into negative x squared. So f prime of x is minus x squared plus 2 over x squared plus 2 quantity squared. So we will look at f prime of x equals 0. A fraction is 0 when the top is 0. When we set this equal to 0, 2 becomes x squared, x becomes plus minus square root of 2. Now we're going to look at this part. F prime does not exist when the bottom is 0. The bottom was not equal to 0 when it was x squared plus 2. Now that you raise it to the power of 2, makes no difference, cannot be 0. It produces no solution. There are two answers, and we should know square root of 2 is about 1.41. Is square root of 2 in between? Yes. Is negative square root of 2 in between? No. There are two answers, only one of them is in between, so square root of 2. Therefore, we evaluate the original function at the endpoints as well as square root of 2. Now, 0 is very simple. 0 over a number other than 0. 0 over 2. This makes it 0, very straightforward. Square root of 2 gives us square root of 2 over square root of 2 squared plus 2. As you know, square root of 2 squared is 2, 2 and 2 is 4, so square root of 2 over 4. And the bottom is 4. The last number is 4, so we have 4 over 4 squared, which is 16, plus 2, which is 18, and it simplifies to 2 over 9. So again, 0 gives you 0, square root of 2 gives you square root of 2 over 4, and 4 gives you 2 over 9. What is the largest number? What is the smallest number? If you have to, you can go with the decimal representation to figure out. Of course, this is the smallest one, and between these two, this is larger than this one. The reason is very simple. Assume almost 4 times 2 is 9. So if the denominator is 2 times, is the numerator also 2 times? No, this is 1.41. So that makes this one the largest. So this is the absolute max. This is the absolute mean. Here's how we do the writing. Absolute max is the square root of 2 over 4, or about 0.35, at the pair square root of 2 and square root of 2 over 4. Absolute mean is 0 at 0, 0. Okay. By the way, just everybody remembers that. This is 0.2 bar in case, I'm sure. Everybody knows that, just as you've seen it before. We're going to continue. We want to find the absolute value. Same situation with this question. The absolute max and mean when f of x is x squared minus 1 quantity cubed, we go from -1 to 2. Obviously, the first thing is what type of a function is that? This is a polynomial function. What is the degree? 2 times 3. So it's of degree 6. Domain is all real numbers. So this is a polynomial of degree 6. Domain is all real numbers. Therefore, it's continuous in the given interval. When we say domain is -2, positive infinity, that means continuous. Okay. And so we are going to find f prime of x. To do so, we put the 3 in front. X squared minus 1 squared times the derivative of the inside 2x. If we put 2x next to 3, we get 6x. So that's f prime of x. So setting it equal to 0 gives us the following solutions. This one is 0, or this one is 0. And x is plus minus 1. So there are 3 answers. Let's see which ones are in between. Is 0 in between, obviously. Is positive 1 in between, obviously. Is negative 1 in between. It's not in between, but it's one of the endpoints you have to evaluate it anyways. So you have to evaluate the function at the endpoints as well as 0 as well as 1. Let's see if we can do this pretty fast. If you put negative 1 here, what do you get? Positive 1. Minus 1 is 0, so that's 0. If you put 0, what do you get? Negative 1. Cube it, negative 1. If you plug in 1, 1 squared, 1 minus 1 is 0, so that's 0. If you plug in 2, 2 squared, let's write that one. You get 2 squared minus 1 cubed. And 2 squared is 4, minus 1 is 3, 3 cubed is 27. So we should have an easy time evaluating those. That shouldn't be a problem. Now, the largest number is the absolute max, which is 27, and the smallest value is the absolute mean, which is negative 1. The writing, absolute max equals 27 at the pair 2, 27, and absolute mean is negative 1 at the pair is equal to negative 1 at the pair 0, negative 1. And I can't emphasize this enough. The way you write it is important. And they may just ask you for the absolute max or mean, or they may ask you for the complete version as I put it here for you. So you want to pay attention to that, the way they ask you to do. Section 4.2, the mean value theorem. We start with what's called the Rolle's theorem. Let f be a function that satisfies the following. Number 1, f is continuous on the closed interval of a to b. Number 2, f is differentiable on the open interval of a to b. A function may be differentiable, but at the endpoints may not be, because of the concept of a limit, okay, from the left and right. F of a equals f of b. The endpoints, they result in the same functional value. If so, then there is a number c in the interval of a to b such that f prime of c is equal to 0. All right, and that's the Rolle's theorem, everybody. Graphs of some typical functions that satisfy the 3 hypotheses are given. Okay. In all cases, we have a continuity. Take a look. This is just a line, so that means f of a equals f of b anywhere you choose. So this is from a to b. this one, the endpoint A and the point B. Again, they're all continuous, okay? And they're all differentiable. That means smooth curve, no sharp corner, no break, no discontinuity. That's all of the above. So because f of A is equal to f of B, then there's a horizontal tangent line in essence. Same thing here. So this happened to have two of them. In each case, it appears that there is at least one point, c comma f of c, on the graph where the tangent is horizontal and therefore f prime equal to 0. And that's really the key. The tangent is horizontal. That's the key, everybody. Example 24, Rolle's theorem, let f of x be x to the power of 4 minus 2x squared. Find all c in the interval of negative 2 to 2 such that f prime is equal to 0. Reminding you that the Rolle's theorem indicates if f is continuous on a to b, closed interval. If f is differentiable on the same interval but open, that means the endpoints are not important, and f of a equals f of b, then there exists, this is how you read it, there exists a c as an element of A and B such that f prime of C is equal to 0. I've explained all those notations before. F is a polynomial of degree 4. Degree 4, everybody. Therefore, it's continuous and differentiable from negative to positive infinity. So if it's continuous from negative to positive infinity, it makes it continuous in the closed interval, any closed interval, including negative 2 to 2. And it's differentiable everywhere. It makes it differentiable from negative 2 to 2 as well. So it's important to understand why it happens, okay? So it's a polynomial, and that's the reason. All right. So we have those two. What is the third one? It says f of a must be equal to f of b. So you are going to plug in negative 2, and you're going to plug in 2 to see what happens. Clearly, if I plug in 2 to the power of 4 is 16. Okay. 2 to the power of 4 minus 2 times 2 squared. And I hope you see that 2 to the power of 4 is 16, minus 2 times 4, 8 equals 8. So we see that, right? For f of negative 2, we do say the same thing. We plug in negative 2. And negative 2 to the power of 4 is also positive 16. This is positive 4 times negative 2 is minus 8. And it becomes 8, which is equal to f of 2 equals 8. Both of them are 8 class. Therefore, Rolle's theorem applies. There must exist a C such that f prime is equal to 0. So what do? We go back to the original function. We take f prime of x. And we set it equal to 0. So this is 4x cubed. This is minus 4x. Set it equal to 0. That means factor out the 4x times x squared minus 1. This gives you 0. X squared minus 1 is 0. By now we know this gives you plus minus 1. So there are 3 answers, all of which are in between. So there happen to be 3 points. All of these numbers are in the given interval of -2 to 2. There is at least a number C that belongs to the interval of a to b such that f prime is 0. There are 3 of them, and any of them in between is acceptable. There are 3 of them. So if thus in the interval of -2 to 2, the derivative is 0 at each of these 3 x values. And so look at the graph, by the way. So this is the graph of x to the power of 4 minus 2x squared, f of x equals that. And so at some point, which is -2 and also +2, they have the same y coordinate, namely 8 at -2, at 2. And in between, look at these points, those 3 points. All of them are in between. If you draw a tangent line for those 3 points, okay, look at that on the graph, of course. So this one on the graph is here, this one on the graph is here, all of them, and you see the horizontal tangent line indicating f prime is 0. So this was the Rolle's theorem. Now, what is the mean value theorem? Let f be a function that satisfies the same as before. Number one, f is continuous on the closed interval of a to b. This is just like the Rolle's theorem so far. Number two, f is differentiable on the open interval of a to b. So far, identical to the Rolle's theorem. Here's the change. Then there is a number c in the interval of a to b such that f prime of c is f of b minus f of a over b minus a. That's the difference. The third part in Rolle's theorem says f of a must be equal to f of b. Because we don't have that, assuming we had, what would happen? If f of a equals f of b, this would become 0, and by the way, a and b are 2 different numbers. Therefore, the denominator is not. 0 over some number is 0, f prime becomes 0. That's the concept. But we don't have that. So, for example, you have this point, completely different y coordinates, right? You have a and b. You connect the two, which is called a secant line. This line, at some point P, which is a tangent line, is parallel to this line. 2 lines that are parallel have equal slopes. That's the idea, everybody. So this one has coordinates a, f of a. This one has coordinates b, f of b. And if you want to calculate the slope for given 2 points, you get this one. The slope of this secant line is this, everybody. And we are claiming there must be a line, because this is continuous and differentiable, parallel to this line, somewhere in between. So in between, for example, part C, you can find that. And so that point is P. So f of b minus f of a over b minus a represents slope of a secant line. In other words, there is a point P where the tangent line is parallel to the secant line AB. That's the meaning of the mean value theorem, which means for the mean value theorem, we are going to write, in short, f is continuous in the closed interval of a to b. F is differentiable on the open interval of a to b. Then there is a number c in the interval of a to b such that f prime of c is f of b minus f of a over b minus a. You may write it in this manner, or you might do the cross product. F of b minus f of a is f prime of c times b minus a. It doesn't matter. Either one is fine. And what is important to notice, Rolle's theorem is a special case of a mean value theorem. What makes it so special? We add the third criterion, which says f of b must be equal to f of a. So this is a more general case. When you set the third one, becomes a specific case, the Rolle's theorem. Let's go with the mean value theorem for this question. Given f of x equals 5 minus 4 over x, find all c in the interval of 1 to 4 such that the slope of a secant line equals the slope of a tangent line. So we have to discuss continuity and differentiability. First and foremost, what type of a function is this? This is a rational function. And here's the graph between 1 and 4. We draw it. We are looking for a line which is parallel to that and the x-coordinate. By the way, there is another line that is parallel to that. You can draw it here somewhere, which you can figure out. But it's not between 1 and 4. That's why it doesn't count. Okay? Just for the sake of argument, if it were between -5 and 4, we would find 12. But in any event, we're going to discuss that in a moment. So we are looking for that point. That's what we are looking for. So that point is somewhere here. We'll figure it out. Number one, this is a rational function. Number two, this function is continuous everywhere except what makes the denominator 0. So what makes x 0? So it's continuous everywhere except at 0. The way we write it, it's continuous from -infinity to 0, union 0 to infinity, and therefore it's continuous in the given interval of 1 to 4. This was given. So that's important to know why we want to say from 1 to 4. Okay? Because that's what they said, from 1 to 4. And so it's also differentiable from 1 to 4. This function, again, is a rational function, differentiable everywhere except at 0. So far, so good. So we got the first one, we got the second one. Then there must be a point where f prime of c equals f of b minus f of a over b minus a. So this is a, this is b. So we're going to find f of 4 minus f of 1 over 4 minus 1. So f prime of c is f of a b, meaning f of 4, minus f of a, meaning f of 1 over 4 minus 1. So if we put 4 in here, class, this happens very fast. So if I plug in 4 here, this becomes 1. 5 minus 1 is 4. So f of 4 happens to be 4. If I plug in 1 in here, I get 5 minus 4, which is 1. So we get 4 minus 1 over 4 minus 1, which makes it 1. So f prime of c is equal to 1. So we are going to set f prime of x equal to that. So what is f prime of x? Let me erase my work and show you. You want to differentiate this. So you are going to write this as f of x equals 5 minus 4 x to the power minus 1. F prime is minus 4 times minus 1 x to the power of minus 2. So it makes it positive 4 over x squared. You set this equal to 1. X squared becomes 4 and x becomes plus minus 2. We have two answers, but the one in between is only positive 2. All right, so between 1 and 4, 2 is in between, and that's the only answer, everybody. Suppose that f prime is between 3 and 5 inclusively. That means 3 less than or equal to f prime of x less than or equal to 5 for all x. Show that f of 8 minus 2 is between 18 and 30 inclusively. And we want to use the mean value theorem. Notice, according to this, you can think of f of b minus f of a. And therefore, this is b, this is a. So a is 2, b is 8. Now, if we go with the mean value theorem, f of x, the interval of interest is 2 to 8, and f is continuous on the closed interval of 2 to 8, and it's differentiable in the open interval of 2 to 8. The question is, why is that? How do we know that? Well, we go back to the question. Suppose that f prime of x is between these two numbers, and that indicates f prime exists everywhere. That means the function is differentiable. If the function is differentiable, it's also continuous, not the other way around. Okay? When the function is differentiable, it's also continuous. So since they mentioned f prime is between 3 and 5 for all x, therefore it makes it continuous and differentiable. So now we are going to go with the mean value theorem, the first to work, and we will make this happen. We also know that f prime is between 3 and 5. That means f prime of c, any number, if f prime of x is between these two, f prime of any number c, okay? So we are given that, right? So f prime of c, which is f of b minus f of a over b minus a, must be between 3 and 5, right? So let's quickly recap. This is really the key. This is given. So it's claiming f prime is regardless between 3 and 5. So f prime of any number, how about c in general, is between the two. So let's replace the a and b with 2 and 8. And of course, 8 minus, so 3 is less than or equal to f of 8 minus f of 2 over 8 minus 2 less than or equal to 5. 8 minus 2 is 6. We are going to multiply all side by number 6. So this becomes 18. This denominator goes away. This becomes 30. So f of 8 minus f of 2 is between 18 and 30. And we just proved what the question was asking. This is using the mean value theorem.